Good to go.
All right, everyone. Thank you for joining our Tech Talk today with the Tech Academy. Today we have Christopher Thompson here with us, and they're going to talk about data structures and algorithms. So thank you, Chris, for being here, and take it away.
Cool. Thanks, Regina. All right. Yeah. So we're going to talk about a topic that a lot of people either skip completely or kind of goes in one ear and out the other. You learn it at the time, you understand it, but that's kind of it, and you never really utilize it again. So for both of those people, we're going to refresh or inform you for the first time. And I'm also going to go into why, right? Because I feel like it's not fully explained a lot of times. And so it's difficult to make that connection as to why you would need these things or why you would use them. So I'll try to give you the why, and we'll also get some resources going at the end to get you going or keep you going on the path to mastering this stuff. So we'll talk about what are data structures and algorithms. We'll do an overview of Big O notation. We'll give examples of data structures, examples of algorithms. Then I give you the why, right? Like, why do you even need this stuff? Like, what's so important about data structures and algorithms? Resources to supercharge your learning journey, and then Q&A. So I'm going to try and get through this presentation. I kept adding things. I tried to stop myself. I tried to delete some slides, so we'll try to make it through as fast as possible so that we can leave time for questions, because I know that there's probably going to be quite a few after I do this. Hopefully I do it justice. So let's get going. So we'll start. What are data structures? A data structure is a way to organize, retrieve, and store data on a computer, right? So there are different containers for data that you can use in your programs when you are coding, right? Building software. Data structures contain information about the values, right? Contained in the data structure, as well as a relationship between the data themselves, right? So there might be some relationship between the values, and usually the relationship, there's at least some sort of organization to the values, right, that you can specify, but it can become much more specific, as in the case of, say, linked lists or something like that, stacks and queues, that kind of stuff. And it's often associated with functions and algorithms that can operate on the data. So it is the case that you can match a data structure and an algorithm to create an optimized program, right, to execute whatever you're trying to accomplish. And we have the data structures broken down into this tree-like structure. So you start at the top. These are all data structures. You come down and you have primitive data structures. So when you're talking a primitive data structure, you're talking an int, a float, a string, right? Data structures that are defined within the programming language themselves. And then you have non-primitive data structures, okay? And those break out into linear and non-linear. So the linear ones, we have something static, right? Meaning it doesn't change. So you declare it and it's there. And that would be something like an array, right? And this is just an array of values, strings, ints, an array of primitive values, maybe an array of other non-primitive values, but it is a static data object. Whereas you have dynamic objects, such as linked lists, stacks, and queues. And by dynamic, we mean they can grow and shrink and change, right, as needed. And so, right, you have with a stack, last in, first out, a queue, first in, first out, those types of things. If you're not familiar with LIFO and FIFO, not terribly difficult concepts, right? Definitely go check those out. We're not going to look at those today, but they're pretty straightforward. And then you have nonlinear data structures. So tree and graph, right? So we're looking at a tree right now. So it would be something like this, right? And then a graph, you can think like a social network. So, I'm friends with Regina, and Regina has friends, and maybe her friend is also friends with me, but also friends with somebody else, right? Like, so you can have this kind of graph, like this social network. Think a social network. That would be a graph, right? You have edges, you have nodes, and they're all connected in various ways. So what are algorithms, right? a lot of times they're explained as recipes, right? But the basics of an algorithm are it's a sequence of steps to solve a particular problem or perform a computation, right? So something happens to some input and it produces an output. The output could be a primitive data structure, it could be a more complex data structure, right? But it has some input, some output, and it takes in data, it produces data, and there's some recipe or function that happens in between to that data based on a set of rules defined by the program. Okay, so those are some basic definitions, and okay, that makes sense. We're storing data, we're acting upon data, but when we're designing these things and when we're deciding what to use, right? Obviously, there's quite a few of them, right? If you look up algorithms, you'll see the same thing, and we'll look at some examples of algorithms later. There's lots of different algorithms to use, and so how do we measure algorithms, right? How do we know when do we say this is the best algorithm or not the best algorithm, right? Or data structure? Well, if I'm running an algorithm, what I care about is the time it takes to execute, right? And I also, you know, the time it takes to execute. I also care about how much space it takes up, right? How much memory it takes up. Through those two things, I want to optimize those such that my algorithm runs wherever I'm planning on it running, with taking up as little space as possible and going as fast as possible. And now there's some trade-offs there. We'll talk about it later. But that's kind of how we're measuring. And when we do measure, right, you're like, well, why don't we just measure how long it takes? If you think about it, right, we have hardware, right? Or how about we just measure how much memory it takes up? Well, maybe I have more memory than my coworkers has, right, on their computer, or my server has more memory than some other server, right? Like wherever this program is going to be running, right? It, you know, it might run faster in terms of time. It would run faster in one place and slower in another place. And so what we want to say is like, we want to compare across all of those, right? We want to not account for CPU and like, you know, different chipsets, different, right? We want to just take that away and say, you know, this algorithm will execute faster than this algorithm, or takes up more space than this algorithm, or less space, or whatever. Okay, we need a way to measure that. Okay, and so we use the measure of time. We measure time complexity, right? So what we're talking about when we talk about time complexity, right, is just in general, when I take an input n, right, let's say it's a list of size 5, right, how does my runtime increase, right? What's the relationship between the time it takes and the input n, right? So as n grows, how does that time grow? We'll look at graphs of that, but that's what we're looking at, the relationship between those. We're not looking at the absolute time it takes to execute, because that can vary. We're not looking at the absolute space it takes up, because that you know, may or may not matter depending on where it's running. Right, so an example would be the input size for a sorting algorithm with an input of 5,000, right, will take longer than an input of size 50, right? So we need to know what that relationship is. And when we talk about that relationship, we use something called asymptotic notation. Now, asymptotic notation refers to the average case, the worst case, and the best case scenarios for an algorithm running. So if you look at this on the x-axis, and I know they don't have numbers on 2 of these graphs, not my favorite thing in the world, but we'll roll with it. So on the x-axis, you see we have an input of size n, right, on all of these graphs. So that's our input. And then on the y-axis, you have time. And so you can see the relationship between the inputs and our function, right, t of n, well, our f of n function, I should say. And what we're looking at here is we can start with, let's start with theta notation, right? So theta notation is the average time it takes for something to execute. Okay, so that's theta is just a function that gives us the average time, right? And so on the graph in the upper right, we see this variable at the beginning, but as things, our n grows, right, and we pass a certain threshold, we see that this line is more or less in the middle with our t of n, which is our theta function that takes in our actual, you can think of f of n as our actual function or our algorithm, right? That time is at the average between the upper bound and the lower bound. You call these tight bounds, right? So the lower bound is the best case execution scenario. The upper bound is the worst case execution scenario, right? So it's accounting for, maybe I'm running on a different system, right? Maybe I'm running on a better system or a worse system, right? And those are those upper and lower bounds. This is what we expect to happen, right? In the best and worst cases. Well, that's great, right? But this average, right? What if this worst case is like really large, right? So our average is like in the middle and we're like, that's cool, except for the fact that when we fail big, right? And when that happens, we have a pretty gnarly problem to solve as developers because it can bring down an entire system. So we're like, okay, well, we didn't account for that worst case very well with the average, right? So, or maybe we over allocated because the best case is much, much lower than we anticipated. So we can also talk about, and not to say that this is, I don't want to say that any one of these is better. There's just one that's more common that we use, right? That makes the most sense in most scenarios. Okay, so we'll talk about omega, right? Omega is the opposite. We're looking at the best case scenario, right? So there's a lower bound. Well, it's not really the opposite. It's the opposite of what we're going to talk about, but this is the lower bound, the best case scenario. So, right, we have some variability at the beginning. As n grows larger, right, we kind of zone in on this, right? So we're like, okay, well, this is the best thing that could happen, but what's the worst? We don't know. It could be really, really bad, right? And you can see this line shoots off into no man's land, and we don't know what the upper bound on that algorithm is because we're not measuring that. And that's not necessarily what we want. We need to know what that worst case is going to be. So what do? Well, we do look at the worst case. And that's what O notation says. It's like, if I'm executing an algorithm, what's the longest it could possibly take? It may not take that long. Like say we're sorting or searching a list for a value, right? If the value is in the first slot and we're linearly searching that list, well, we're going to find it instantaneously. That's great. But what if it's not in that first? What if it's at the very end of the list? And that means we have to search every single value to get to that value. That's n. So that means that we'd be searching the entire length of the list n times, right? And so we use this O notation. We're going to show what this is, right? This is all very hand wavy right now. I'll show you what this is, but it talks about the worst case running time. What's the worst possible thing based on what I'm looking for or what my algorithm is trying to get to, the output it's trying to get to. What's the worst, right? And I think that's clear. Hopefully that's clear. If you have questions, we can go over that at the end, but we're going to keep clearing this up by looking at this. So this is O notation. So you'll often see it written like this, a capital O, and then you'll see some sort of number, right? A function in here, a number or a function, right? Or a value, let's call it a value. So we start at constant time, right? No matter what my n is, no matter what is happening, as my n grows, it will always take the same amount of time to execute. What's an example of this? If my n, right, let's say I take in n and my function or my algorithm just adds 1 and then returns the result, right? Well, no matter whether my n is 1 or whether my n is 1,000,000, we're still executing the same operation. We're adding 1, right? So it will always take the same amount of time. So that's an O of 1, right? Constant time complexity. And then we have O log n. So we can see that here, that logarithmic time, right? When our n is small, right? And as it grows from there, it grows pretty dramatically at the beginning, right? But as our n gets larger and tends towards infinity, we tend towards this horizontal asymptote, right? And we get infinitely closer to that asymptote. So we get to this log n. So at some point, we reach a point where no matter how large our n grows, it's actually taking less and less and less and less and less time to execute. So for a large n, we like that, right? Log n is great. And then we have linear. So one-to-one relationship. As n increases, our time increases, right? So you can think of a linear, like I was talking about that linear search where you search a list all the way through, right? every time we increase n, our worst case is that our time will increase by a certain amount, right? And so on and so forth. So that's a linear relationship. And so we denote that by just a straight 45-degree angle, right? O of n. And then we get up, right? We get n log n, we get n squared, cubed, and then exponential. And you can see those, did they not get, well, n log n will just increase log n by n as n increases, right? So that'll just grow larger, 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 larger. That's not pictured here, but that's what would happen. And you have n squared, n cubed, and then your your exponential. So we'll take a look. How do you evaluate an algorithm, right? Like, what does that look like? So I'm going to go through some pretty simple examples, but the concept is the same, even if it gets more and more complex, right? So we'll start with just a simple for loop. And this is Python. Hopefully it's fairly readable. Usually people don't have a problem reading Python, so I went with Python. So for I in range n, so we're just saying n values, right? So it could be 5, could be 100. But for I in range n, we're going to print hello world. So we'll print hello world n times. That's all it's doing, right? So we loop through that. Well, what does that look like? Okay, well, when we print hello world, right? That's no matter what happens, printing hello world will always take the same amount of time. So that's an O of 1, right? That executes an O of 1 time, printing hello world. But we have this for loop, right? So that executes n times. So if at the worst, we're going to execute this n times, right? This loop. And so we end up having our function, our time function, t of n, is equal to a constant, our print statement, times n, which is our loop, right? O of n. Now, since this is a constant, the n will dominate that at high as n grows. We don't really care, right? As n tends towards infinity, and this is what we always talk about, is dominant terms. This is how we come to our O of n. As n dominates, right? C is a constant, right? Like, we don't really care about that. Thus, we can drop the C. We don't have to say O of C of n, right? We just say O of n, because the worst case scenario, and in this case, it will always be the worst case scenario, that it executes n times. So now we have a double for loop, right? So we can do the exact same exercise. Print statements O of 1, executes the same amount of time every time. Our for loop J will execute n times, so this is O of n. But we also have an outer for loop, right? That wraps the whole thing and will also execute O of n, right? So for every n, we execute n times. What does that look like as an equation? Our time function n is equal to our constant c times n, which will execute n times. So we go, for each n, we execute this j n times. Therefore, we have n times n. So n times n times, which gives us n squared. And that's when you can say that we have O of n squared. That's not ideal. There's usually better ways to come down from that. Hopefully that's not what your algorithm is doing. Okay. We won't talk about optimization technique. Well, I shouldn't say that. We talk about it a little bit in this talk, but there's lots of optimization techniques. And if you're getting exponential or quadratic time or cubic or whatever, right? Like, definitely you should be looking for a better alternative to what you're doing. Sometimes it's inevitable, but definitely try to look for that better alternative. Now, this case is really interesting, right? So, well, I shouldn't say really interesting. It's more interesting. So we have a for loop, just like the first for loop we executed. Pretend this is a function. This will always run, right? Let's pretend that. Now we have this second double for loop, right? So this first for loop executes. We already know O of n times. The second for loop that's wrapping another for loop we know is O of n squared, right? So we have a C1, our print statement, times our n, executes n times, plus C2 plus this, right? So our n squared, which we pull that term down to here. We simplify that a little bit. We say it's n squared. Well, as n tends towards infinity, right? Let's say n is 1 billion, right? Well, 1 billion's a lot, right? We're like, oh God, 1 billion, right? N, that's a lot. But when we come over here and we have n squared, right? We realize that what's 1 billion squared? That's a very large number, right? And all of a sudden, as we tend towards higher and higher numbers, this term will begin to dominate. And it ends up being the case that we don't actually care about this n term over here as much. So really, we're going to call this O of n squared. Okay. Hopefully that makes sense to folks. A little mathy. I tried not to get too mathy. We can get much more mathy, but I'm going to keep it pretty light here. So let's talk about space complexity. So with space complexity, we're talking about the amount of memory required, right, to execute your algorithm. Now, why would we need memory? Well, first of all, we need the input, right? We have the input, but we also have maybe intermediate values that are being executed and stored as we're executing our algorithm. And then, and that also can create temporary data, right? And then our outputs, and we do something with those outputs. So space complexity is especially important when you have a program that's going to have high memory space. So when we're talking about big data, so I work a lot with big data. We use things like Spark, and you've probably heard of, Spark, Hadoop, MapReduce, all that kind of stuff. When you're dealing with those things, right, it's very important, right, to think about memory, especially if you have finite amount, and even if you don't, right? If we're in the cloud, well, we have a lot of memory, right? But that costs money. And so we're always thinking about how can we minimize that? All right. So we'll look at some algorithms now. And you can see here, I put this chart up so that we can kind of look at, you may not know what these algorithms are, but now that we've done O notation, you can start to compare across these algorithms, the best, the average, the worst case time complexities, and then also space complexity, right? So we can see these, let's compare something, right? We have quick sort and bubble sort, right? Now our bubble sort has O of 1 space complexity, which is sweet, right? And now when I said we usually look at the worst case, when you look at the worst case for a lot of these, you see O of n squared, right? But a lot of times it actually turns out that, with these algorithms, like quick sort is usually what's used in, say, a sorting algorithm, at least in Python. When you say sort this array, it's actually quick sort working behind the scenes. I believe it's still quick sort. And your average case, right, is actually better than any of these others, right? And you have log n space complexity, right? So when I say we usually look at O notation, it's important, but it's also not the only, which is why I also introduced these other ones, right? It depending on your use case, and the thing with tech, right? It always depends. There's no universal, like, this is the way you do it all the time, right? But O notation is commonly what people are looking at. In terms of quick sort, like what algorithm do we use? Well, at worst, it'll be this, but at worst, so will all of these. But the average we'll get is actually better than bubble, insertion, select, and we get better space complexity as compared with merge sort and time sort. So we're going to go with quick sort, right? Based on the average case that we're expecting, the expected value, right? And so what do sorting algorithms do? Well, they put a list or an array in a particular order. The values can be numerical or lexicographical, meaning A, B, C, D, E, F, G, right? And can arrange in ascending or descending order, used to optimize the efficiency of other algorithms. What do we mean by that? Well, we also have searching algorithms, and we'll get to those, and we're going to take a look at some visualizations of those. Sorting algorithms, it can be the case that a searching algorithm is actually more efficient than another searching algorithm, but only if the values are sorted first. So a lot of times you want to use the best sorting algorithm you can paired with a search algorithm versus just using the best search algorithm, right? Sometimes you get better results. It depends, but that is the case many times. And so if we take a look at this graph here, so I love these visualizations. We're going to look at a few of these. They're really fun. So what we do is we randomize an array of values. So we have this array of values. I don't know how long it is. It's pretty long. I didn't want to do anything too large. And so we can look at each algorithm, right? So let's look at insertion sort. So insertion sort is doing its thing. There's an algorithm working to put these values in order, and we can visualize that here. We see it's slowly working its way to the right. I'm going to skip forward because it takes a while. Eventually, you see all these values are sorted. Well, that's great. Insertion sort was taking a little while. Let's see selection sort, right? So selection sort's going through, also doing its thing, right? But also taking quite a bit of time. We skip forward, right? And we can keep going. Let's go to quicksort, right? Which I was talking about, where the average case is actually better than most of these, right? And it takes up less space. So what we can do, oh, I forgot. excuse me, and randomize it first. There, need something to sort, excuse me. So you'll see quick sort actually works quite quickly, and we can watch this one till the end. So notice these two red lines. I don't know if you can see those at the bottom. So this is using something called a two-pointer technique. Okay, and a two-pointer technique is a technique that you use to sort and search different arrays of values. It's a very popular technique and can be very useful, especially in like coding interviews and stuff when you need to do stuff quickly. Many times you're going to a two-pointer technique. So you can see it got sorted and how much faster it looks like it was going to be. We didn't let the other ones finish, but I assure you it's faster than some of those other ones. So the array, the values are sorted. Great. We visualize that, and again, we have already. Let's go back a couple. We've already seen the time complexities and stuff on that. So hopefully you make that connection, right, between the visual. Right, we could see that the time complexity was actually better for quick sort in n log n, and we couldn't really measure the space, but yeah, it's obviously better based on this O notation. Okay, so cool. We can sort things. We can also search for things, right? Maybe we have a big, pile of stuff, right? Whatever it is, int strings, other data structures, and we need to find something, right? Well, we use search algorithms. And we retrieve an element from a data structure. And there's two types, right? We do sequential search, which we've already mentioned, which is a linear search. It looks through every element till it finds it, right? Not the most efficient, okay? And there's interval search, right? So we search in data structures that are sorted. So that was what I was talking about, where we pre-sort the values, and then it's more efficient to search them after that, right? We can use something like binary search. Right, so let's take a look at binary search. Or linear search. Okay, so I'm gonna do an example here. So our value at the beginning is 70. So we're gonna look for the value of 70. And this is kind of a contrived example, and maybe you're like, okay, cool, Chris. Right? Notice we find it immediately with linear search, right? Because we get to that very first value instantly. Great. Is binary search faster? No. Right? So linear search is actually faster if our value is in that first slot. But that's not always the case, and that's not what we want to look at. That's the best case scenario. What's the worst case scenario? Right? Worst case scenario, it's value 996 in slot 31. Right? With linear search, we got to search every single one, and we get there after 31 iterations. Right? What happens with binary search? Done. We did not search. I don't know how many iterations. Did it say how many iterations? No, it doesn't. It's less, right? Maybe we could do it with, let's try 778.
Hey, Chris,
Yes.
sorry to interrupt, but is there a way to actually zoom in a little bit?
Oh, yeah. Okay. Potentially. Is that good? Better?
Yeah, better. Maybe a little bit more. Just a bit.
Okay.
There we go. Perfect.
Okay, cool. All right, I'll have to scroll up and down a little bit because it doesn't quite fit on my screen, but that's cool. Right, let's try it. There we go. Cool. All right, so let's do, what are we gonna do? 778. So we'll do a linear search. It's gonna take 24 iterations. Cool. Let's go binary search. Done. Right? I don't know how many iterations that was, maybe 10, maybe less. Right? So depending on where it is in the array, right, will dictate how long it takes. But you can say, right, that usually, right, using binary search, and if we make this real large, right, we have this many values. Let's try using 770, which is sitting in slot 142. Right, linear search, we already know, right? I'm not going to do the linear search, but binary search, quick, right? Whereas if we had gone linearly, that would have taken us 142 iterations. Right, so you can see as the n grows, binary search dominates linear search, and it happens pretty quickly. Hopefully that made things pretty clear with the searching. Okay, so we've got sorting, we've got searching. I'm going to pull out good old Fibonacci. It's the easiest example, and you'll see it everywhere, right? What is Fibonacci? Fibonacci is something that's found in nature, right? It's a sequence of numbers found in nature. Very interesting. Definitely go check it out. It looks like this, right? We have f of 0, right, is 1. F of 1 is 1. F being just, a Fibonacci number in the sequence, right? The sequence is always 10. So f of n, any number in this sequence besides f of 0, f of 1, can be derived from f, or f, I should say f of 0. It is equal to f of n minus 1 plus f of n minus 2 for all n greater than 1. So there's a 0, this is the 0th slot, 1, 2, 3, 4, 5. So any slot can be computed just by computing the f of n minus 1 plus f of n minus 2. If we're trying to get like the 5th element, well, we need to compute the previous 2 elements. Well, what are those elements? We need to compute the previous 2 elements, and so on and so on and so on, right? And we can visualize that through, oh, where's my tree? Well, we'll get to the tree. So this is what the algorithm would look like, right? So we say, define fib. Your input is n. If n is equal to 0, we return 0. If n is 1, right? And this is the number of Fibonacci values that we want to give out, by the way. So n is not, right, it's how many Fibonacci numbers, right? Or I should say the nth Fibonacci number. So we got 0, we got 1, and actually this should be 1. I think I messed this up. Well, anyway, the 0th element should be 1. My bad. So less than or equal to 1 should return 1, and then else we're going to n minus 1, right? So this is what's called a recursive call. Okay, so we're recursively calling the same function in itself, and what happens is it dips down. It goes all the way down until it hits. This is called a base case. Once it hits that base case, it folds back in on itself, returns all those values back up the tree, and you end up with your final result, right? So this is calculating the nth Fibonacci number. And we can see that played out here. The nth Fibonacci number without DP. What's DP? Dynamic programming. We'll talk about that in a sec, right? So we have fib 6. So we're calculating fib 6. What do we need to calculate fib 6? We need fib 4 and fib 5. What do we need to calculate fib 4? Fib 2, fib 3, right? What do we need to 5? Fib 3, fib 4, so on and so forth, all the way down, and we get to this base case, fib equals 1, right? Okay. So what we can see here is that we actually have overlapping problems, right? So they call these overlapping subproblems. What's an overlapping subproblem? Well, we're actually solving the same problem over and over and over and over and over, right? Fib 1, fib 1, fib 1, fib 3 it appears both here and here. Also here, we have fib 2 appearing here and here and here. So we end up solving the same problem over and over and over. Isn't there a better way? Yes. We use dynamic programming. What dynamic programming does is it stores the values, the intermediate values. So remember we were talking about memory space, okay? Keep that in mind. So we're storing intermediate values, which takes up memory. But what we're doing is we're trading off memory for time, right? So by storing these values, we don't have to recompute them. So what we do with this is called memoization. We can take an input n, but we also have a dictionary, okay, which is a hash table. So oftentimes in a lot of these programming problems, you'll find that a hash table is actually the thing you want to use to optimize an algorithm, right? So you're storing intermediate values so you don't have to recompute them. You just look them up because the lookup speed of a hash table is O of 1, right? So we decrease the time complexity by using a hash table. So we have these same base cases, right? Which are actually correct. I realize it's because it's 0 indexed, so I'm good. Else, right? Our else statement is the important part. If n is in our dictionary already, if we have already computed that value, we just return the value, O of 1. So we can say this line takes O of 1, right? And then we calculate from there, and we carry that. This is another recursive call, right? And we carry that dictionary that we have with us, right, to every single call, right? So memory will grow because we have overlapping subproblems, but we don't have to compute those subproblems. So actually this is more efficient, right? And this ends up taking, I should have put it, O of n at worst. Yes, okay. Worst case scenario, O of n, there's no overlapping subproblems. Okay, I believe. Someone correct me if I'm wrong. I forgot. And then we also have, okay, so I didn't really add this in the slides. There's two forms of dynamic programming. We have tabular, we have memoization. So there's a top-down approach and there's a bottom-up approach. What does that mean? Well, the top-down approach, and we can actually, let me see if I didn't. The top-down approach is we're storing values and we're computing along the way. So we start at the top of the tree, and as we calculate things, right, we store those values. We carry that dictionary forward, and then we just do the lookup. The bottom-up approach starts with the base case. It starts at the case that n is 0, and we store that, and then we work our way up the tree. Okay, so in that case, we're calculating every value, but in calculating every value, right, we don't have to branch out, and it can be faster. Okay, so usually tabular is a faster way to do it. The problem with tabular, right, the bottom-up approach of calculating first, and let's go back to our tree to see what we mean. So we start with this case and work our way up versus starting with this case and working our way down. It's harder. It's harder a lot of times to figure out what the proper approach is to make sure that you're only calculating those values once all the way up the tree, right? So we're still using a dictionary. We're still getting that O of 1 lookup, and it can be faster, but you really have to think about that. So it's a much more difficult process. So if you don't, the rule of thumb that I've heard is if you need to calculate every sub value, then you use tabular, the tabular idea of dynamic programming, where you calculate each of these all the way up. If you don't need to calculate every value, right, then you can use memoization. That's usually the rule of thumb with that. You can look up, there's lots more to say on that. You can go look it up. I had an example. I don't know where it went. Let's see if we can find it. Let's go real quick. I'm going to try and zoom through the rest of this so we can get to questions, because I know there's probably questions. Let's go to algorithm visualizations. This is a great website. I'm just going to copy and paste this into chat so everybody can go play, because it's super fun to watch these. Have fun. We're going to go to dynamic programming. We're going to calculate the nth Fibonacci number. Okay, so we can see here, this is just a straight up Fibonacci recursive, right? So let's calculate the 10th Fibonacci, 10th Fibonacci number. Fibonacci recursive. Here we go. Okay. One thing about recursive calls, and another thing about tabular that I will mention, that bottom-up approach, is you can oftentimes use a for loop in the bottom-up approach versus using a recursive call. Why is that important? Well, a lot of times there's a limit on recursive calls. It also takes more memory, and it takes longer to make recursive calls versus doing a for loop. And that's why tabular can be faster, or is faster, can be faster than using the memoized approach of recursive calls with a dictionary. Okay, so that took quite a while. This is the same as tabular, right? Bottom-up approach, boom, 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 boom. Okay, you can see how fast that is. Here's the memoized approach. Notice we go all the way down and all the way back up. That's what I'm talking about, the top-down approach. And then we return all of those values back up the stack. Okay, so the table starts at the bottom, goes one way. Memoized has to travel down and back up, returning those values. And that's what I was trying to get at with that top-down and bottom-up approach. Okay, zooming right along. We did that, looked at this. Here's our tabular, that's great. All right, why do we learn data structures and algorithms? Right, there's several reasons, right? The first one, you want to pass those FAANG interviews. That's what I hear the most, right? They're like, oh, they test me on data structures and algorithms, and I'm like, okay. And they're like, well, it's not fair. I hear this, it's not fair. It's not a fair way to test me. And I'm like, well, it may not be fair in your eyes, but I'll say this. There's someone out there who did pass the interview and did get the job, right? And I don't think, it's probably not the case that they're smarter than you or some super genius. I've seen, there's a great example, a Tech Academy graduate named Nixon Martinez. I watched Nixon go and try to get into Microsoft. He failed the first time. Why did he fail? He failed the data structures and algorithms test. So what did he do? He took 6 months. He went back and day and night studied data structures and algorithms. every day. And he went back and he now works at Microsoft. Okay. So it wasn't that Nixon was not as smart as these other people. It's just that he needed to study more. The more effort you put in, the more you're going to get out. So if you want those jobs, if you want those big salaries, if you want to work at Amazon or Google or wherever, probably not Twitter at this point, but any one of these large companies, right? Put in the time, learn this stuff, just do it. It's probably worth it. You know what I'm saying? If you want the big bucks. All right. Now, what are the other reasons, right? I'll tell you, when you're a developer, right? A lot of times there's different measurements for a good developer, right? But it's very likely that the less time you take to solve problems and the more accurate you are, right? The more efficient your programs are, the more productive you'll be. The more productive you are, the more you'll shine at your job, right? If you know this stuff and someone else doesn't, you can solve a problem in half the time that they can because you know your data structures and algorithms and software architecture and all of the other things that come along with being productive. That's great. Like, that's a great reason to learn it, right? And when you are more productive, right? And I'm going to skip down really quick. You build better software, right? When you know this stuff, and it takes you less time, and it equals quality for your users, but it also means you build more cool stuff. You get to do more cooler stuff. If it takes you a long time to solve problem A, but someone else solves problem A, B, C, D, E, right? They get to experience more. They get to build more. They get to have that feeling and anyone who codes knows the feeling of solving a problem and seeing it work, right? They get to experience that more. And if you want to experience less frustration, there's patterns to this stuff. You don't have to reinvent the wheel. All software can be broken down all the way to these data structures and algorithms, right? It's just different combinations of architectures and patterns built into different things to solve different problems. If you can solve those sub problems, right, it builds up to you being able to solve larger problems and doing it faster and doing it better than others, right? And that's good, right? And it gives quality to your end users. Your users, I've seen so much bad coding out there, you guys. And there's software sitting out there in production right now that's terrible. And people complain and whatever. And it's just it's not a good experience, right? So put out quality, put out the quality you want to see in the world. I don't know, some kind of Gandhi quote, quasi Gandhi quote for programmers. But okay, the other thing I want to touch on, you're going to save your company money, right? If I'm a startup, I just want to get code out there. I just want to get a product out there because I'm trying to just get to market, right? That's a different scenario. If you want to work at a Google, if you want to work at Zillow, if you want to work at any of these companies, that time complexity we've talked about, that space saving complexity, that equals dollars, right? That equals money. The scale that they're working at, that n squared versus log n complexity or whatever, that could be hundreds of thousands or millions of dollars you're saving the company, right? And that is well, say what you will, it's a good thing, right? If you're an employee, you probably don't want to cost the company hundreds of thousands or millions of dollars, right? So by learning this stuff, you're able to optimize your software, optimize your code, and actually save the company money in the long run, which is good. Okay. That's why they want to test you on this stuff. They don't want inefficient coders because that will actually cost them money. So yeah, they're paying you $250,000, but you're also costing them in addition another, whatever, 100,000 or whatever it costs for you to write inefficient code for them. They just don't want it. They don't have the budget, right? And we'll get to the questions. I'm almost done. I just wanted to touch on, we have books and courses. These are five of some of the books that I think are going to be the most useful for beginners and just in general, right? So we have Algorithms 4th edition, right? That's for Java and C++ folks. Grokking Algorithms, classic, uses Python, lots of pictures. It was from somebody who came from a liberal arts degree or a fine arts degree, I think. And so there's lots of cool pictures and diagrams, very useful for getting started. Definitely not your end, but it'll get you on the path in the right direction. Data Structures and Algorithms in Python just came out in 2022. So this is one of the newer books. I think that's going to be really useful. It's great. It has a lot of color diagrams and things. Big fan of diagrams when it comes to, as you saw, the visualizations when it comes to learning this stuff. I think it's really good to be able to visualize what's happening. And then cracking the coding interview is a classic that you can use for studying if you do have an interview at any tech company, including the big ones, right? This will get you where you need to go. 189 problems and questions and solutions. I don't know that there's a specific language they use. What I will say is I've taken classes that were in JavaScript. I don't write JavaScript, but it's actually really useful. I coded in Python, right? When I was taking a JavaScript algorithms and data structures course. And like, that was actually cool because I couldn't just copy their code, right? Like I actually had to think it through and do it in my own language. So it might be more helpful to read it in another language and try to implement it in your own. And then extra credit to whoever does Introduction to Algorithms 4th edition. That is a 1,200-page textbook, very, very comprehensive. So it's the theory, it's the practical, but it is 1,200 pages. If you can make it through that, you'll probably be in pretty good shape by the end. But extra credit, it's not necessary, but it is one of the most popular textbooks for this stuff. 4th edition just came out recently. Okay, I've also included link, and oh, by the way, for those of you that have the slides, these are all links to these books. So the different places you can buy those books. Of course, you can just get it on Amazon, but I tried to link to like the publishers. Algorithms 4th edition is free. I tried to push free stuff. So Algorithms 4th edition is available online completely free. All the code is free, all the exercises, they have everything is free. It's really, really great. So it's from Princeton. They have a course that I also listed here. It's the Coursera course, part 1 and 2, algorithms, that pairs with that book. So they pair together really nicely. So if you follow the book and these courses, the Coursera courses aren't free, but if you use that book, you'll be in really good shape, from Princeton University. Algorithms and data structures, here's my free push. Free Code Camp, their YouTube channel is insane. They have so much stuff on their YouTube channel, and freecodecamp.org, I think that was my first coding thing. They have great tutorials from data analysis to front-end development. Definitely check them out. Master the Coding Interview. Zero to Mastery is one of my favorite Udemy like content producers. Great stuff. Definitely check out Master the Coding Interview. It walks you through exactly what you need to know to master the coding interview, right? And then data structures and algorithm specialization, very in depth from UCSD. UCSD is a very well-renowned computer science school. So this is a 6-part series, I think, maybe longer. Data structures and algorithms, very comprehensive, theory heavy, math driven, but don't be scared of that. Right, you can learn that stuff. So definitely check that out if you're interested in like a specialization, like a comprehensive specialization. And I already mentioned the algorithms part 1 and 2. Okay, that's the end. We're ready for questions. Hopefully we have enough time.
Yeah,
We
great
do have enough
Chris.
time.
Go ahead, Regina.
I was just going to say thank you, Chris, for that great presentation. And then I was going to ask Rick, I see someone has their hand up. Maybe we could unmute their mic to see what questions they have. And then I also have some questions in the chat as well.
Okay. Prasad, I'm opening up your microphone, so go ahead and ask your question. It's open now. Did you have a question, Prasad?
Make sure to unmute your mic.
Well, you can leave your question in the chat, Prasad, and we'll get to it. Let's go ahead with the questions in the chat. Hey, Chris, I did have a question for you.
Sure.
With storage, like time complexity and storage complexity, they're both very important. But with storage becoming so big now and so huge and ubiquitous, would you say like time is more important now with getting your with solving, you know, whatever you're trying to solve?
Again, I come back to that thing where it's like it depends, right? You don't want unnecessary. I mean, storage is cheap. Like let's say blob storage, very cheap, right, for companies, and that's great. And there's lots of solutions being built around blob storage because of that being cheap. But nevertheless, like when I'm executing a program, like on a VM, right? I'm paying for that use of that VM and the memory and the memory and the compute. Those are the two things you pay for with a VM. And so I want to optimize my program to minimize the amount I'm using, because if I'm using 1,000 VMs, if my program can execute in and use less storage, right? Again, it comes down to that thing where if I'm talking about like one VM, not a big deal, right? But as that memory footprint grows, or as the data grows and I need more memory, right? I want to minimize that, because that can get real expensive, right?
Yeah.
Like, because you with the compute, right? You just, the VMs especially, those are hard to manage. You don't want to, it's hard to like keep scaling up and down these VMs. There's other ways, right? Like things like Kubernetes and things that'll handle a lot of this scaling for you, but nevertheless, always good to like try to minimize that. But again, it depends on the situation. If I'm dealing with big data, maybe that's what I'm optimizing for, is space. But then if I'm trying to compute some values, not necessarily big data, and feed those back to users don't want to wait a long time. These are contrived examples, but nevertheless, I think it makes the point, right? It just depends on your situation.
Yeah, no, it definitely makes sense. And I try to focus, my focus is more on time now, but I guess I'm not dealing with a lot of big data.
Right.
But it's both are important. So
And then
go ahead with the questions, Regina.
So Chris looks like has a question which he had earlier. So let's unmute his mic and
right.
All right. And yeah, okay, the mics are open.
All right. Thanks again. Appreciate it. Great presentation. I'm going to have to review it a few times, but that old argument between algorithms being, the O notation and time and space complexity being so critical that it's either a hire or no hire. How much of it can be learned? Because there's a lot of front-end engineers, a lot of iOS engineers who don't really do a lot of this work, or maybe it's been a while because they're kind of deep in the UI or something. What are your thoughts on that?
I mean, the only way, just like with any like tech thing, but programming in general, is just a hammer on it. And like if they don't look, there's tons of companies out there that don't require you to know this stuff. My last 3 jobs never tested me on this stuff, right? They just asked me about my like core knowledge and had technical discussions about whatever, right? And so I was filling a gap or a need on their team that did not require me to know algorithms and data structures. It required a different skill set. So if your skill set is such that you're filling a need and maybe the company won't require you to know this stuff. But if the company is requiring you to know this stuff, you have to just assume that the reason is because they need that skill set, right? If you don't want to work for a company that tests you on that, like, don't work for the company. I don't really know what to say. Like you can't change the company. This is just a reality that we live in. So if you really want that job, back to your question about, can anybody learn this? Yeah. I mean, honestly, you don't need a strong math background to have, logical thinking, right? This is all logic when it comes down to it. You just need to learn the tools and techniques, right? It's very rare, unless you're looking at one of these textbooks or something, it's rare that you see any math notation at all. It's mostly just theory and implementation. So in my opinion, yeah, I think anybody who learned to code can learn this stuff. It's just, it takes time. It's hard. It's very hard.
Well, thank you. Appreciate it.
Absolutely.
Well, and Chris, some of the attendees may not know what a FAANG company is, so you may want to let them know.
Right. So, well, it's kind of, I don't even know if it matters anymore, because Facebook is now Meta, and Twitter is dying, and I don't know, whatever.
Yeah, it should be May. It should be May now.
The main companies. It's Facebook. Was it FAANG? Dang it, FAANG.
Apple.
Apple. Thank you.
Amazon.
Yeah, Amazon, Netflix, and Google, the
Yep.
FAANG companies. And there's some additions to that, like the Twitters and Zillows and Ubers of the world tend to copy the interview process. The interview process is always the same, by the way. I can lay it out for you right now. Okay. The interview process, you'll go through a recruiter. The recruiter will screen you. If they think you're a good fit, they set you up. You do 5 interviews or so. There's usually 2 to 3 problem-solving interviews, meaning coding challenges. There's 1 architecture interview where you go through, they give you a scenario, you have to like give them the answer, what you think, and then there's a behavioral or like I should say a cultural fit, right? Like just evaluating if you're cool or whatever. I don't know. Just
If you're cool.
yeah, if you're cool or not. Right.
Yep.
And so they take all these things into account. So that is the FAANG interview, right? And that's what most of these courses that talk about cracking the coding interview, mastering the coding interview, that's what they're talking about. They're talking about this FAANG process that most companies that are like dealing in large data and big distributed systems are gonna be talking about. So the Ubers, the Netflix, so on and so forth.
Gotcha. Prasad, the mic is open. If you want to ask your question, go right ahead.
Oh dang.
Okay. Let's go ahead with the chat questions.
I think he's asking the question, but we can't hear you, Prasad. So maybe there might be an issue with your mic.
Let's go ahead with the chat questions, Regina.
Oops, sorry, I put my mic on mute accidentally. To go back to the question, so Andrew, you also had a similar question about the mathematics. Let me know if that was answered. If not, I can ask this question. But let's see. So does it matter the programming language you use for these interview tests? So
no, not in my experience with these tests. It's never mattered. They're just like, what language are you comfortable with? I've just done Python every single time. That's pretty much all I use. Yeah.
Next question. Would you say that algorithms and data structure are pretty core principles to machine learning engineering as well?
Where are we at? ML. Can you say that one more time? Sorry. Oh, I see it. Would
you say that?
Yeah, I would say that. I mean, there's specific, right? ML is obviously has its specific algorithms and so on and so forth, but that you need to know. But more and more these days, they're wanting data scientists, but machine learning engineers to build software. And so if you're anytime you're building software, like you should really have this stuff down, right? Yeah, I agree, Wesley. Like, I think just if you're doing any kind of technical work beyond just like a data analyst or anything like that, it's probably useful to know. More and more, they're going to want what's called a full stack ML engineer or a full stack data scientist, right? And so just knowing as much as humanly possible, right? It can't hurt. Let's just say that. I wanted to jump back and Prasad left. Okay, well, Prasad had a point to make, and I wish I would have made it before they left. But today we're discussing distributed programming, right? And these structures will help only on the linear side, not on parallel distributed programming side. Right. Oh, back. Prasad's here. Okay, so Prasad, you're correct. Yeah, there's other tools and techniques to deal with distributed programming. But this is an introduction to data structures and algorithms, and I only had an hour. Maybe we can do a part 2, but this will get you going, right? And that stuff needs to be, that can be learned, but you have to get the basics before you can move up to start talking about, parallel and distributed programming. That's what I'd say on that. And Prasad also said, Java makes sense. And yes, Java is another language that you can use. I was just saying I use Python. They just have asked me what language I use, and they let me use whatever on there. So depends on your interview, depends on what you're interviewing for.
Got it. And then that last question, referring back to Python, it says, I heard Python allows for completing these tests faster, but that Python as a language has insufficiencies that don't fare well in regards to big O questions. Not really a question.
Yeah, there's this thing that came out not that long ago that talked about how slow Python is, right? And all of a sudden everybody was like, Python's too slow for this or that or the other thing. And it's like, well, first of all, Python's making changes that will make it dramatically faster now in Python, where are we at, 1.2 or whatever it is now. But besides that, right, there's companies including Google and what's another one, Pinterest, and a lot of big tech companies that use Python, right? A lot of their stuff is built in Python. So if it's good enough for Google, it's probably good enough for an interview question. You know what I'm saying? Like, again, it just depends, right? Python is a tool, Java is a tool. All of these are just tools to solve problems. So if your problem is solved better by a different tool, that's fine, you know? But in terms of the programming interviews, I would just say go with what you're comfortable with. If you learned Java, go with Java, right? Like, as long as they allow it, right? And it's always good to pick up a lower level language like a C++. Python under the hood is C, well, unless you're running Jython or whatever it is, and it's Java. But nevertheless, you know, picking up these compiled language, right, is very good. And I think you should, everyone should learn that stuff. It'll make you a better programmer. Do you need it? No. Will it make you better? Like, you could get by only knowing Python. You could probably have an entire career based on Python. You know what I mean? Like there's all these things like, should I learn this and should I learn that? Just go with what you're comfortable with and go with what the job needs. And that's it, you know. Don't try to take on too much. Once you learn one language, honestly, you can pick up any other language. Like, I had to write something in Go not that long ago. I'd never used Go. So I used Go, right? Like, built this thing in Go, great, it works, you know, and it's pretty easy to pick up. It took me a few weeks to get the basics and I was able to be productive, you know. But it just depends on the situation.
So following that up with this, do you see that last question? Do you think that a strategy of lower level and higher level languages is good for targeting these interviews?
I think it's overthinking it by trying to, like, it just matters that you solve the problem. Right? Now, understanding the limitations maybe of the language you're using, right? Or its benefits over another language, that could help you in the interview, right? They might ask you, you know, about that kind of stuff. But if one person does it in Java and the other person does it in Python, does that mean the person who did it in Java is better, or that they're going to get the job over the person who did it in Python? No, like, probably not. So, yeah, like, and I see, yeah, Prasad is talking about Java and Scala, and like, that's only if you need that stuff. I honestly do all my big data in PySpark, and we do tons of jobs for different clients, and they're perfectly happy with us using PySpark. If you know Java, that's great too, you know, using Scala and stuff, that's awesome. If it's needed, right? There's sometimes that it is needed, but the vast majority of things can be done in whatever, right? Like there's certain very specific use cases that I've found where, you know, we've had to, like I said, I had to write something in Go. And really that was only because the rest of it was written in Go. Had it not been written in Go, we probably could have used Python. We probably could have used Python anyway, but there were some opinionated people and we went with Go, right? There's lots of cool stuff being written in lots of languages. Right. Yeah. I honestly, Prasad, I've never had to go to the JVM level. Like, if you're staying on a surface level and just know your PySpark, like, unless you're debugging like the JVM, that's what PySpark's for. You know what I mean? I mean, we could have this conversation all day. See, this is what I mean. Like, there's like strong opinions about it. You should know this and you should know that. And that's what I'm trying to distill down is like, in terms of just learning data structures and algorithms, learn that stuff, master it, be able to pass the coding interviews. It'll make you a better programmer in the end, right? And when you're a better programmer, you put out higher quality stuff. You're able to progress in your career faster, right? And there's always going to be a different or way of doing things. There's always going to be someone who thinks something else is better. But this will help you pass for sure. And just get to a higher level, that next level of understanding.
Really good points, Chris.
Yeah.
And are there more questions, Regina?
So I don't see any. So let me know if you have another question. We are over time as well, however.
Yeah.
So Chris, would it be a good place to connect with you on LinkedIn if people have further questions?
Yeah, totally. You can connect with me on LinkedIn.
I have it right here. So
oh, perfect.
or wherever else you want people to connect with you. Also, so like I said, next week we don't have a tech talk due to Thanksgiving. So the week after we will, and it's going to be a job placement Q&A, and it's going to be with our job placement staff, me, Rick, and Dalton, who is actually working with a bunch of our instructors. So you can ask questions about our curriculum if you do have any questions on that, and you can check that out here. But again, it's not next week, the week after. November 2nd. Also, we are recording this talk and we're going to post it to our YouTube channel later today. So if you want to watch this back, here is a link. And I know that some people joined in later. So if you're looking for Chris's presentation, here's a link for that in case you didn't get to see it in the chat. Other than that, thank you all for joining. Thank you so much, Chris, for joining us for another great talk. Hope to see you in another one very soon. But thank you all, and I hope everyone has a great weekend and happy early Thanksgiving.
Cool. Yeah, thanks everybody.
Yeah, thanks, Chris. Great presentation as always. And have yourself a great Thanksgiving, okay?
Yeah, you too. Thanks everybody.
All right.
Yep,
You guys
Thanks,
have a
Chris.
great one.
Yeah, you too. Thanks everyone for coming out. Have a great Thanksgiving, and we'll see you soon.
Also, hey, Wesley, but back to you. Rick, we have Wesley signed up for another